Welcome to Number Theory. Today we are exploring a fascinating concept called primitive roots of composites. Imagine having a massive ring of keys, but you want just one master key that can open every single locker in a hallway. In the mathematical world of clock arithmetic, a primitive root acts exactly like this master key. Let us dive in and see how it works. To understand this master key, we first need to look at clock arithmetic, also known as modulo arithmetic. In this system, numbers wrap around after reaching a certain maximum value, just like the hours on a clock face. A primitive root is a special number in this system. When you repeatedly multiply this number by itself, it generates every possible valid number in that clock system before finally looping back to the start. Now that we know what a primitive root does, let us define what makes a number valid in our clock system. A valid number is one that is co-prime to the clock size, meaning they share no common factors other than the number 1. For instance, if our clock size is 10, 3 is valid, but 4 is not because both share a factor of 2. We count the total number of these valid numbers using a mathematical tool called Euler's totient function, written as phi of n. This brings us to the mathematical definition of our master key. The formula shown is based on Euler's theorem. Here, G represents our candidate for the primitive root, and n is the size of our clock. The symbol phi of n tells us exactly how many numbers are co-prime to n. The formula guarantees that raising any valid number to the power of phi of n will always bring you back to the number 1. However, a true primitive root will not hit the number 1 any earlier than this exact step. Knowing what a primitive root is, we must ask, do all composite numbers have one? The answer is no. This formula is the primitive root theorem for composite numbers. It tells us that a composite number n will only have a primitive root if it perfectly matches one of 4 strict shapes: the number 2, the number 4, a power of an odd prime p, or twice a power of an odd prime. If a composite number does not fit into this exact list, it is mathematically impossible for it to have a master key. Let us see this theorem in action with a concrete example. We want to find out if the composite number 9 has a primitive root. First, we check its shape. 9 is 3 squared, which perfectly matches the allowed shape of an odd prime raised to a power. Because it matches, we know a primitive root must exist. Next, we use Euler's totient function to count the valid numbers. The calculation shows there are exactly 6 valid co-prime numbers for a clock size of 9. Since there are 6 valid numbers, our primitive root must take exactly 6 steps of multiplication to reach 1. We will pick a small test number, 2, and start multiplying. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. All of these results are smaller than our clock size of 9, so no wrapping around is needed yet. We have found 3 distinct valid numbers, and the pattern is building nicely. Continuing our test, 2 to the 4th power is 16. Because 16 is larger than 9, we wrap it around by subtracting 9, leaving a remainder of 7. 2 to the 5th power is 32, which leaves a remainder of 5. Finally, 2 to the 6th power is 64. Dividing 64 by 9 leaves a remainder of exactly 1. Because it took exactly 6 steps to reach 1, the number 2 has successfully generated all 6 valid numbers. Therefore, 2 is officially a primitive root of 9. To truly understand what just happened, let us look at this visually. This diagram proves why the number 2 is a master key for the clock size of 9. Notice how multiplying by 2 forces you to jump from one valid number to the next in a perfect unbroken circle. No valid number is skipped and no number is visited twice before the cycle finishes. This complete unbroken circle is the visual definition of a primitive root. If we had chosen a bad key, the circle would have closed too early. Now that we have seen a successful master key, let us examine a composite number that fails to have one. We will test the number 8. 8 is 2 cubed. Looking back at our theorem, the base is an even prime, not an odd prime, so it does not match any of the allowed shapes. The theorem predicts that 8 will not have a primitive root. To prove this prediction, we calculate phi of 8, which is 4. The 4 valid numbers are 1, 3, 5, and 7. For a primitive root to exist, we need to find a number among these that takes exactly 4 steps to reach 1. Let us test them. We start with 3. 3 squared is 9, which wraps around a clock of size 8 to leave a remainder of 1. It reached 1 in only 2 steps, not 4. Next, we test 5. 5 squared is 25. Dividing by 8 leaves a remainder of 1. Just like the previous test, 5 reaches 1 in only 2 steps. Finally, we test the number 7. 7 squared is 49. Dividing 49 by 8 gives a closest multiple of 48, which again leaves a remainder of 1. Every single valid number reached 1 in just 2 steps, completely failing to reach the required 4 steps. This proves mathematically that the composite number 8 has no primitive root, exactly as the theorem predicted. You might wonder why these unbroken cycles matter outside of pure mathematics. Understanding which composite numbers have primitive roots is absolutely critical in modern computer security. When you send a secure message online, your computer often uses a system called public key cryptography to lock the data. These security systems rely on the predictable, unbroken cycles generated by primitive roots to mix up the data so hackers cannot read it. If a programmer accidentally chooses a composite number that lacks a primitive root, the security cycle will be too short and easily broken. We have covered a lot of ground today. Let us review the most important ideas. A primitive root is a special number that can generate every valid number in a clock arithmetic system through repeated multiplication. While all prime numbers have these master keys, composite numbers are much pickier. A composite number will only have a primitive root if it takes the specific form of 2, 4, a power of an odd prime, or twice a power of an odd prime. By understanding this rule, we ensure our digital communications remain safe and unbreakable.